In October 2017, a telescope in Hawaii picked up something moving through our solar system. That, by itself, is not unusual. Telescopes detect thousands of objects moving through space every year. Asteroids, comets, chunks of rock drifting through the void. Scientists log them, name them, file them away. But this one was different. The moment astronomers began to analyze its trajectory, its speed, its shape, and its behavior, the room went quiet. Because this object had not come from within our solar system, it had come from somewhere else. For the first time in recorded history, humanity had detected an object that had originated in another star system, traveled across the vast emptiness of interstellar space, passed through our cosmic neighborhood, and was now leaving, never to return. They named it Oumuamua, and the more scientists studied it, the more confused they became, because Oumuamua did not behave like anything they had ever seen before. It did not look like anything they expected. And when they tried to explain it using the laws of physics they understood, those explanations kept falling apart. What was Oumuamua? Where did it come from? Why did it move the way it did? And why, years later, does the scientific community still not have a definitive answer? Today, we are going to go through everything we know, everything we don't know, and why this single, strange, briefly glimpsed object may be one of the most important things our species has ever discovered. To understand what made Oumuamua so shocking, you need to understand what astronomers were doing when they found it. The Pan-STARRS telescope, the Panoramic Survey Telescope and Rapid Response System, sits near the summit of Haleakala Volcano in Hawaii, at an altitude of over 3,000 meters. Its job is to scan the sky continuously, night after night, looking for anything that moves. It is specifically designed to hunt for what scientists call near-Earth objects, asteroids and comets that might be on a collision course with our planet. It is one of the most powerful sky survey systems ever built, capable of scanning the entire visible sky multiple times each week. On the 19th of October, 2017, a researcher named Robert Warwick was reviewing data from the previous night's observations when something caught his eye. A faint point of light moving across the sky. That was not unusual. Pan-STARRS detects thousands of moving objects. What was unusual was the way it was moving. When astronomers detect a new object, one of the first things they calculate is its orbit. Using the object's current position, speed, and direction, they trace its path backward and forward through time and space. They determine where it came from and where it is going. For asteroids that originate within our solar system, those calculations produce a familiar result. The object has an elliptical orbit, a curved path that loops around the sun, constrained by our star's gravitational pull. Even comets, which can travel on very long elliptical loops, ultimately remain gravitationally bound to our solar system. But when Robert Warwick ran the calculations for this new object, the result was something that had never appeared in any astronomical record. The object was on a hyperbolic trajectory, not elliptical. Hyperbolic. That single word changed everything. A hyperbolic trajectory means the object is moving so fast, too fast, to be gravitationally bound to our sun. It is not looping around, it is passing straight through. It came from outside our solar system. It is moving through our solar system, and it is leaving. Warwick immediately flagged the discovery. His colleagues ran the numbers again, then again. The result was the same every time. This was not one of ours. For the first time in human history, we had detected an object from another star system passing through our cosmic backyard. The astronomical community scrambled. Telescopes around the world were redirected. Observations were collected as fast as possible, because everyone understood one thing immediately. This object was not going to slow down. It was not going to stop. Whatever it was, it had already made its closest approach to the sun on the 9th of September, 5 weeks before anyone noticed it. By the time astronomers were alerted, it was already accelerating away from us, heading back out into the darkness between the stars. The window to observe it was closing. Fast, the race was on. Before we go into what they found when they studied it, let us pause for a moment on the name. The International Astronomical Union, the body responsible for naming objects in space, established a new naming convention for this discovery. Since it was the first confirmed interstellar object ever detected, it needed a new category. They designated it with the prefix 1I for first interstellar object. Its full designation is 1I/2017 U1. But scientists also gave it a common name, drawn from the Hawaiian language in honor of the telescope that discovered it. Oumuamua. In Hawaiian, the word roughly translates to a messenger from afar arriving first, or scout. Some interpretations suggest it means reaching out toward something distant. The name felt appropriate in ways nobody initially intended, because Oumuamua had indeed arrived first. It was the scout, the first confirmed visitor we had ever detected from the galaxy beyond our solar system. But the word messenger would take on a more loaded meaning as the mystery deepened. What message, if any, had it brought? And from whom? Those questions would divide the scientific community in ways that few astronomical discoveries ever have. As astronomers scrambled to observe Oumuamua before it disappeared, they began to piece together its physical characteristics. And what they found was deeply strange. When you observe a distant astronomical object, one of the tools available to you is the way its brightness changes over time. As an object rotates, its different faces reflect different amounts of sunlight toward the telescope. By measuring these variations in brightness, scientists can deduce the object's approximate shape. For most asteroids and comets, these brightness variations are relatively modest. The object is roughly round or slightly potato-shaped, and the changes in brightness reflect that. For Oumuamua, the brightness variations were unlike anything ever recorded. The object was cycling between extremely bright and nearly invisible on a regular, rhythmic basis. The amplitude of the variation, the difference between its brightest and darkest measurements, was the largest ever recorded for any known solar system object. When scientists modeled what shape could produce these readings, they arrived at something extraordinary. Oumuamua appeared to be extremely elongated. Not somewhat elongated, not cigar-shaped in the casual way people describe things, but dramatically, almost impossibly elongated, with a length-to-width ratio estimated at somewhere between 5:1 and 10:1. Think about what that means for a moment. Picture a cigar, Now stretch it. Keep stretching. Now imagine something that long, tumbling end over end through space, alternately presenting its broad face and its narrow edge to your telescope. That is what the brightness data suggested. Nothing like it had ever been observed in our solar system. Comets are not shaped like that. Asteroids are not shaped like that. The formation processes that create rocky or icy bodies in solar systems do not naturally produce shapes with those proportions. The scientific community offered explanations. Perhaps it was a fragment, a shard broken off from a larger body by a catastrophic collision in another star system. The violence of such an impact could theoretically produce unusual shapes. Perhaps the shape was being exaggerated by the observations. The measurements were taken under difficult conditions as the object was faint and moving fast. There was uncertainty in the data. Perhaps we simply had not seen objects like this before because we had never been looking in interstellar space. All of those were reasonable suggestions, but the shape was just the beginning. As Oumuamua departed our solar system, astronomers continued tracking it for as long as they possibly could, and they noticed something that stopped everyone in their tracks. Oumuamua was accelerating, not decelerating, not maintaining speed, accelerating. This requires some explanation because it sounds deceptively simple. Of course, an object moving away from the sun would change speed. The sun's gravity is pulling on it, which slows it slightly on the way in and then assists it on the way out. But when astronomers calculated exactly how much Oumuamua should be accelerating based on the sun's gravitational influence, the actual acceleration was greater than the prediction. Something else was pushing it. In astronomy, when an object accelerates beyond what gravity alone can explain, there is a well-known and well-understood cause: outgassing. When a comet passes close to a star, the heat causes frozen material on its surface, water ice, carbon dioxide, other volatiles, to vaporize and jet out into space. These jets act like tiny thrusters, pushing the comet in the opposite direction. This is called outgassing, and it is a completely normal part of cometary behavior. Astronomers know how to account for it. They observe the jets, measure the gases being released, factor them into their models. It is understood physics. So the natural first assumption was that Oumuamua was a comet from another star system, outgassing as it was heated by our sun and being pushed along by that process. Perfectly reasonable, except for one problem. There were no jets. Oumuamua showed absolutely no signs of outgassing, no visible jets, no coma. The cloud of gas and dust that typically surrounds a comet's nucleus as it heats up. No cometary tail. Every telescope that looked at it saw a clean, dark, featureless object. No gas, no dust, no jets of any kind. So if there was no outgassing, what was causing the extra acceleration? The scientific community proposed several explanations. Perhaps the outgassing was happening, but releasing gases that were invisible to our instruments. Carbon monoxide, for example, or molecular hydrogen, substances that would not show up clearly in the observations available at the time. That was plausible. It was also convenient. Critics pointed out that proposing invisible outgassing as an explanation felt circular. You cannot see it, therefore it could be anything. Therefore it explains everything. Others proposed a different explanation entirely, one that proved far more controversial. In November 2018, a scientific paper appeared that sent shockwaves through the astronomical community and then, rapidly, through global media. The paper was authored by Shmuel Bialy and Abraham Loeb. Abraham Loeb was not a fringe scientist or a UFO enthusiast. He was, and remains, the chair of the astronomy department at Harvard University. One of the most prominent and respected astronomers in the world. The paper proposed that the most natural explanation for Oumuamua's anomalous acceleration, given the complete absence of outgassing, was radiation pressure from the sun. Sunlight, it turns out, exerts a tiny but measurable push on objects it strikes. This effect, called radiation pressure, is incredibly weak. For most objects, rocks, comets, large chunks of anything, it is so small compared to other forces that it is effectively irrelevant. But for a very specific type of object, radiation pressure could become significant. A very thin object. If Oumuamua were extraordinarily thin, like a sheet or a sail, then even the faint pressure of sunlight could exert enough force to cause the observed acceleration. The paper calculated the required dimensions. To explain the acceleration through radiation pressure alone, Oumuamua would need to be no more than a millimeter thick, possibly much thinner, and it would need to be extremely light for its size. The paper then made the observation that would ignite the controversy. An object that thin, that light, that large in surface area relative to its mass does not occur naturally. No known natural process creates objects with those properties. The paper concluded, carefully, with appropriate scientific hedging, that one possible explanation for Oumuamua's properties was that it was an artificial object, a light sail, possibly a piece of technological debris from another civilization, possibly a probe, possibly something we had no category for. The world exploded. Headlines screamed alien spacecraft. Social media erupted. News anchors asked astronomers if we had finally made contact. Loeb himself was calm and precise in interviews. He was not claiming Oumuamua was alien. He was saying that of the explanations available, the artificial object hypothesis was no less scientifically supported than the others, and in some ways fit the data better. He would later write a book about it, titled Extraterrestrial. In it, he argued that the scientific community was too quick to dismiss unusual hypotheses out of fear of ridicule, that the stigma around searching for extraterrestrial intelligence was causing scientists to overlook evidence that deserved serious consideration. His colleagues were not universally enthusiastic. Many astronomers pushed back sharply. They argued that invoking alien technology as an explanation for any unexplained phenomenon violated a core principle of scientific reasoning. You do not jump to extraordinary explanations when mundane ones remain available. The molecular hydrogen explanation was proposed and vigorously debated. A team of scientists suggested that Oumuamua could have been a fragment of a nitrogen ice body, a type of material that would outgas in an invisible way while behaving chemically differently from ordinary comets. Others suggested it was a fractal, porous body, a very low-density cloud of loosely bound material that would behave differently from solid objects. None of these explanations were entirely satisfying, and meanwhile, Oumuamua kept moving. farther and farther from the sun, fainter and fainter in the telescopes. By early 2018, it was beyond the orbit of Saturn. By mid-2018, past Uranus. By 2020, it had passed Neptune. It is now irretrievably gone. We will never see it again. No telescope we currently possess or are likely to build in the coming decades would be capable of detecting it at these distances. Whatever it was, it has left us, and it took its secrets with it. Let us step back from the noise and the headlines and go through what the scientific community has actually established. Not speculation, not hypothesis, the hard facts. Oumuamua was real. It was observed by multiple independent telescopes across the world. Its existence and its basic properties are not in question. It was the first confirmed interstellar object ever detected passing through our solar system. Its trajectory was definitively hyperbolic. It arrived from outside our solar system, passed through, and departed. This is not in dispute. It was elongated. The brightness variations were real and significant. The object had an unusual shape by the standards of everything previously observed in our solar system. It showed non-gravitational acceleration. Something caused it to depart from the trajectory predicted by gravity alone. This is measured, real, and unexplained by simple physics. It showed no signs of outgassing that could be directly observed, and it was moving too fast to have originated nearby. Tracing its path backward, astronomers calculated that it came from the direction of the constellation Lyra, specifically from the vicinity of the star Vega. However, because it was moving so fast relative to our solar system, it is unlikely to have originated at Vega specifically. More likely, it has been drifting through interstellar space for hundreds of millions of years since being ejected from whatever system it formed in. That last point deserves to sit with you for a moment. Oumuamua may have been traveling through the empty darkness between the stars for hundreds of millions of years before it encountered us. Launched from a solar system that may no longer exist, or whose star may have died long ago. It drifted through the void alone for longer than complex life has existed on Earth. And then, for a brief period of weeks, a blink in cosmic time, it passed close enough to our sun to be warmed by it. We had just barely built the technology to notice if pan-stars had not been running. If Robert Warwick had been looking at a different part of the sky. If the object had passed through our solar system 50 years earlier, before such instruments existed, it would have come and gone without a single human being ever knowing it was there. We got extraordinarily lucky. Oumuamua raised an obvious and urgent question. If one interstellar object had passed through our solar system, were there others? The answer came faster than anyone expected. On the 30th of August 2019, an amateur astronomer named Gennady Borisov, working from his private observatory in Crimea, discovered a new comet. At first, it appeared to be a standard comet, a fuzzy blur of light with the beginnings of a tail. These are discovered fairly regularly by both professional and amateur astronomers. But as more observations came in and the trajectory was calculated, the result was immediately familiar. Another hyperbolic orbit. Another interstellar visitor. This one was Is, officially named 2I/Borisov, the second interstellar object named after its discoverer. Borisov was immediately different from Oumuamua in one crucial way. It looked like a comet. It had a coma. It had a tail. It showed visible outgassing. Its behavior was consistent with an icy body being heated by the sun and releasing volatile material. In fact, with the exception of its interstellar origin, Borisov looked almost completely normal. Scientists analyzed its composition and found water ice, carbon monoxide, and other materials that match comets within our own solar system. This was both reassuring and fascinating. Reassuring because it suggested that at least some of the building blocks of solar systems, icy bodies, volatile compounds, the raw material of comets, appear to be universal. What forms around our sun also forms around other stars. Fascinating because it made Oumuamua look even stranger by comparison. Borisov was weird in one way: its origin. Everything else about it was familiar. Oumuamua was weird in every way. Its origin, its shape, its lack of a coma, its mysterious acceleration, its unusual surface properties. Borisov gave scientists a kind of baseline. This is what an interstellar comet looks like when it is a normal interstellar comet. Now look at Oumuamua again. And Oumuamua still could not be explained. Here is the thing that keeps astronomers up at night. We detected one interstellar object, Oumuamua, essentially by accident in a narrow window of observability before we had any systematic way of searching for them. Then we detected a second one, Borisov, within 2 years. What does that tell us about how common these objects are? Scientists have done the mathematics. If interstellar objects are rare, if they are exotic, unusual things that only pass through our solar system once every million years or so, then the probability of us detecting two within 2 years of each other, essentially by chance, would be vanishingly small. The much more likely interpretation is that interstellar objects are extraordinarily common. Models suggest that there may be thousands of interstellar objects passing through our solar system at any given moment. We simply cannot detect most of them because they are too small, too dark, and moving too fast. The galaxy, in other words, is full of debris. Every star system in the Milky Way likely ejects material during its formation. Comets that come too close to a giant planet get flung outward at escape velocity. Asteroids collide and fragments scatter into interstellar space. During the chaotic early period of any solar system, enormous quantities of material get thrown out into the void. Over billions of years, across hundreds of billions of stars, this adds up to an unimaginable quantity of material drifting between the stars. We live in a galaxy that is, in some sense, constantly exchanging matter between star systems. This has profound implications. It means that material from other solar systems, including, potentially, complex organic molecules, the building blocks of chemistry, perhaps even frozen microbes clinging to the surface of a comet, could be traveling from star system to star system, scattered by the physics of orbital dynamics. Life, or the ingredients for life, might be moving through the galaxy on the surfaces of interstellar rocks. This idea, called panspermia, is not new. Scientists have discussed it for decades, but the detection of Oumuamua and Borisov gave it new relevance. These are not theoretical objects. They are real. They have been detected. They passed through our solar system. The galaxy is not a collection of isolated islands. It is a connected system, with material flowing between its billions of stars across billions of years. And somewhere in that flow, there may be messages we have not yet learned to read. The story of Oumuamua is not over, in sense. Fact, in some ways, it is just beginning. The Vera C. Rubin Observatory in Chile is scheduled to begin full operations in the coming years. It is a next-generation survey telescope with capabilities that dwarf Pan-STARRS. Where Pan-STARRS could survey the sky multiple times per week, Rubin will survey the entire visible sky every 3 nights. Its sensitivity is far greater. Its field of view is enormous. Scientists estimate that Rubin will detect a new interstellar object roughly every year, possibly more frequently. Each of those detections will be an opportunity that Oumuamua did not fully give us. The chance to observe an interstellar visitor in detail over an extended period before it disappears back into the void. There is also a more ambitious proposal. A mission concept called Project Lyra has been studied by a group of aerospace engineers and scientists. Their question was simple. Could we chase Oumuamua? The mathematics are brutal. Oumuamua is already so far away and moving so fast that reaching it would require a spacecraft launched on a trajectory that is at the very edge of what current physics allows. You would need a massive rocket, a close flyby of the sun to build up speed using its gravity, and then a journey of decades. Even under the most optimistic scenarios, a spacecraft launched today would not catch Oumuamua for approximately 20 years. And when it arrived, it would be in the dark of interstellar space, billions of kilometers from the nearest star. The mission is possible. It is extraordinarily difficult and expensive, and the debate about whether it is worth pursuing continues. But the question itself is remarkable. For the first time, humanity is seriously asking whether we should chase an object that came from another star system. The fact that we are even having that conversation shows how much has changed since October 2017. I want to take a moment away from the data and the hypotheses and the academic debates, because Oumuamua is not just a scientific puzzle. It is a mirror. For most of human history, we have looked up at the night sky and seen a beautiful, static backdrop. Stars that have always been there and always will be. A universe that is, in some fundamental sense, separate from us. Out there, distant, untouchable. Oumuamua did something to that picture. It arrived. From out there, from the space between stars that we had always assumed was empty and unreachable, an object came. It moved through our solar system. It passed close enough to our sun to be warmed by it. In some sense, it touched our world, and our world touched it. And then it left. It is now heading back into the darkness, back into the interstellar void. In 1,000 years, it will be passing through someone else's solar system, or no one's. In 1,000,000 years, it will still be drifting, as it has been drifting, perhaps for hundreds of millions of years already. Whatever it is, a fragment of rock, a shard of ice, a piece of nitrogen frozen solid, or something we have no category for. It has been on a journey of almost incomprehensible duration and distance. And for a few weeks in the autumn of 2017, it crossed paths with a species that had just barely learned to look. What strikes me most about the Oumuamua story is not the alien hypothesis, not the controversy, not the academic arguments about molecular hydrogen and radiation pressure and nitrogen ice. What strikes me is the narrowness of the window. We have had telescopes capable of detecting something like Oumuamua for a very small number of years. We happened to be looking in the right direction at the right moment. We had just enough time to observe it before it disappeared. If we had begun this era of sky survey 50 years later, we would have missed it entirely. In the vast sweep of time, in the billions of years of Earth's history and the billions more to come, the window in which we were capable of seeing Oumuamua, and actually did see it, is extraordinarily, almost miraculously narrow. That is worth holding on to. The universe is vast, time is long, and we are here, right now, at exactly the moment when we can begin to see what is moving through it. That is not a small thing. Oumuamua has gone. We watched it arrive from the stars, pass through our solar system, and return to the interstellar dark. We studied it with every tool available to us. And in the end, we were left with more questions than answers. Was it a rock shaped by ancient collisions in a distant solar system? Was it a comet of an unusual type we had simply never seen before? Was it something else entirely? An object with properties we do not yet have the physics to fully explain? We do not know. But here is what we do know. The galaxy is not empty. Material moves between stars. Objects drift through the void on journeys spanning millions of years. And occasionally, one of those objects passes close enough to a small, blue planet for the creatures living on it to look up and notice. We noticed. For the first time in history, we detected a visitor from another star system and watched it pass. We may not know exactly what Oumuamua was, but we know it was real. We know it was here, and we know the galaxy is full of others like it, or unlike it, that we have not yet seen. The next interstellar visitor is already on its way. We just have to keep looking. If this video changed the way you think about the space between stars, consider subscribing, because we are just getting started. I'll see you in the next one.